we considered any right triangle, what are the possible values of theta? Could it be 0? So greater than 0, less than 90. We're going to extend that. We're going to extend the domain of sine, cosine, and tangent beyond less than 90, greater than 0. Yes. And after today, in a couple more days, we're going to extend it even further. In fact, we will extend the domain of the sine function to include all real numbers. So you can plug in any angle, no matter how positive or negative it is. Yeah. So you could do 90, and you can have a right angle that's 1,000,000 degrees. So stay tuned. So this worksheet says, in the 17th century, farmers used a common unit to survey their farmland. This unit was called a rod and is equivalent to 16.5 feet today. A ladder of length 1 rod is resting up against a wall, and it's slowly pulled away from the wall at its base. During this motion, the top of the ladder slides down the wall as the base of the ladder travels away from the wall. This creates a right triangle with the ladder, the wall, and the ground as sides. So we'll call this the wall, from the ground to the top of the ladder. From the wall to the bottom of the ladder is the ground, and then we have the ladder. And theta, today, and for the rest of the chapter, theta will always be the angle created at the intersection of the ladder and the ground, always. Okay? So this makes a bunch of triangles. We start No, that's what we're doing. That's where we're headed. Yeah. So here are the triangles. We start vertically, and the angle created from the ladder to the ground is 90 degrees. So theta is 90 degrees, but there isn't a triangle. Does everybody get that? Then as we pull the ladder out, theta gets smaller, the wall gets smaller, the ground gets longer, until eventually the ladder lies on the ground, and theta becomes 0 degrees. So theta starts at 90, and as it shrinks down to 0, then the ladder moves down the wall until it hits the ground. Okay? As soon as the ladder hits the ground, we stop, because pulling the ladder away from the wall doesn't make any sense. All right, turn the page. So for today, we're going to eliminate the normal descriptions of these right triangles. So this was H, this was O, and this was A. We're not going to talk about those anymore today. Instead, we're going to call this the ladder, and this is the wall, and this is the ground. So in terms of this situation, what is the sine of theta? Wall divided by the ladder. Yes. What would the cosine equal? Ground over the ladder, and the tangent? Wall divided by the ground. So cosine is the vertical distance divided by the hypotenuse. Or no, sine is the vertical divided by hypotenuse, and cosine is the horizontal divided by hypotenuse. That's important, and it's going to stay that way for the rest of this chapter. Okay? All right, let me go down a little bit. So we have two lengths to find. We have a particular triangle, 37-degree angle for theta. The ladder is 16.5 feet. How do we calculate the height of the wall? How do we figure out what this is? Sine, wall over ladder. So the sine of 37 is x over 16.5. Is this a multiply or a switch? Multiply 16.5 times the sine of 37, and I get 9.92 feet. Hopefully this is review. How do we calculate the length of the ground? Cosine of 37 equals x over 16.5. What kind of problem is this? Multiply. Now, we could have used the Pythagorean theorem and we could have used the tangent, but I want to do cosine. So 16.5 cosine of 37, 13.17. As long as you don't round the decimals, it's not going to matter which way you do it, no matter how you calculate it. Right. If you plug 9.92 into the Pythagorean theorem, your answer is going to be a little bit off. That's true. Well, have you guys ever heard of significant digits? Significant digits are incredibly complicated. I don't know how to use them. It depends on how many numbers there are in your answer, how close it will be. If you round to 2 decimal places and you show your work, you'll never miss an answer on a test. Okay. But really, there's a scientific way to use the correct number of decimal points, and I've seen it twice, and I don't understand it. I asked Moss about it, and he doesn't get it either. It's really complicated. So we don't mess with it in high school. Okay, so we have the side lengths. Let's consider what is the sine of 37. So I plug sine of 37 in, I get 0.6018. What does that mean? It's not, well, I guess you could say it's the steepness of the ladder. That would work. But what does it mean as a number? Well, no, it's not. The steepness would be 37. I lied. What does 0.60 mean in this? Proportion. What if we use percentage? What does 60% mean in this story? Nope, it's not the tilted. The wall length is 60% of the ladder. It's not the grade. It's the length. So Connor would kill for a D minus. So if I were to take 9.92 and divide it by 16.5, I should get 0.60. So 9.92 divided by 16.5, and that's off a little bit because I rounded. So if theta is 37 degrees, the length of the wall is 60% as long as the length of the ladder, regardless of the size of the triangle. Yes. To find the percent, just type in the sign. Okay? That's the first great lesson today. Right. So the answer is just, so it means that the wall is 60% of the ladder. Yeah, that's the answer. The wall is 60% of the ladder. Now, if I did the cosine of 37, what does that mean? The ground is 79% as long as the ladder. So if I divided 13.17 by 16.5, I should get 0.798. And I do. Okay? So that's the first important thing. The sine and the cosines simply give you percentages. So, how big can these percentages be? Up to 99.999. How low can they get? 0.00000001. Ah, so we're going to extend this to include 0 and 90 degrees. That's half the lesson today. So, it can. All right, well, what if I switched units? So instead of 16.5, what if I used 1 rod? How tall is the wall going to be? Don't touch your calculators. 5.6. It's 60% of 1. What is the ground going to be? 0.79. Now, let's actually calculate that. So if I wanted to calculate the wall, the sine of 37 equals the wall divided by 1. Well, how do I get rid of that 1? I either don't, because W over 1 is W, or I multiply by 1, in which case 1 sine of 37 is just a sine of 37. So that number now has two meanings. It's a percentage and it's also a length. Okay? That's the second great lesson for today. No, it doesn't have anything to do with rods. It depends on the hypotenuse being 1. Okay? So in a right triangle, in this particular right triangle, if the ladder is length 1, then the height of the wall is equal to the sine of theta. Okay, we'll write that down in a second, but just let me point that out. This number is both a percentage and a length. The only time that happens is if the ladder is length 1. Well, what if the ladder is 17.825? I don't know any units that are equal to 7, whatever I said. But if you want, you just call it 1 Colette Mackelprane, make up your own unit, and then the ladder is length 1, and that makes the sine and cosine problems easier. So from now until the end of the chapter, we're going to go ahead and make every ladder length 1. Because if the ladder is length 1, then we save ourselves doing some calculations, and the percentage and the side length are the same number. Well, that has another effect. If the ladder is 1, then this number has a double meaning. It's a percent and a length. It's 60% and 0.6, whatever units you're using. So if you look at the top of the next column, yes, the percentage will change as the angle changes. But the percentage is the same as long as the triangle is similar. So what we do is we take any triangle and shrink it down till the ladder is 1, or blow it up till it hits 1. And then the calculations are easier. Right? If all similar triangles yield the same ratios, we might as well pick the triangle that makes the math easy. So, do we prefer ladder length 16.5 or 1? We definitely like 1. Here's the reason. There are two reasons. The percent equals the length. That's the first reason. And sine becomes easier. Sine is wall over ladder. Just sit on my desk. But what if the ladder is length 1? Sine of theta equals the wall. And you're done. So you don't even have to draw the triangle. All you have to do is push sine, enter the angle, and that will tell you the height of the wall. Okay? And likewise, the cosine of theta equals the ground. What about the tangent? What is tangent? Wall over ground. So does the tangent care how big the ladder is? No. So this only affects the sine and the cosine. Okay. What is the value of theta before the ladder begins to move? So in this picture, the angle created from the ladder to the ground is 90 degrees. But the side lengths still exist. How tall is the ladder in this problem? Well, 16.5 or 1. I choose 1 because it's easier. What is the height of the wall? 1. What is the length of the ground? 0. Which is why we don't have a triangle. But we could still measure 0, right? You put a tape measure up there. Oh, no length. It's a 0. Okay? For the next story, we pull it all the way out till the ladder hits the ground. What is the angle? 0 degrees. What's the height of the length of the ladder? 1. Height of the wall. 0. Length of the ground. 1. So now we're going to calculate the sine of 0, the cosine of 0, and the tangent of 0. Move those over. So, if the ladder is length 1, sine is wall. If the ladder is length 1, the sine of theta is the height of the wall. You can divide them if you would like, but you don't need to. If the ladder is anything other than 1, you have to divide by ladder. So, well, you have these They're right here. So sine of 0 degrees. How high is the wall at 0 degrees? 0. So that makes sense. The height of the wall at 0 degrees is 0% as big as the ladder. In your calculator, if you type in the sine of 0, you get 0. Okay? What is the cosine of 0? So the length of the ground at 0 degrees is 1. Or, as a percentage, it would be 100%. At 0 degrees, the ground is 100% as long as the ladder. And the only way to do that is to crush your right triangle. So if I type in the cosine of 0, I get 1. What about the tangent of 0? Well, tangent is wall over ground, so it would be 0 over 1, which is 0, which means the wall is 0% as long as the ground. If I type that in, I get 0. Okay, let's go the other direction. Sine of 90 degrees. So the height of the wall at 90 degrees is 1. So the what? How do we talk percentages? What is 100%? Compared to wall to ladder is 100%. So if I type in the sine of 90, I get 1. Okay? Cosine of 90, because the length of the ground at 90 degrees is 0, 0%. Yeah, you have answers. Yeah. I just didn't have room to do it all. Ah, tangent of 90. What does that equal? 1 over 0. Why? What? So, as a percentage, yeah, describe this as a percent to me. 1 is infinitely bigger than 0. Right. And here's the reason. If I had 1 over 1, how many 1s are there in 1? 1. If I had 1 over 1/2, how many 2s are there in 1? 2. If I had 1 over 0.1, how many 1/10ths are there in 1? 10. See the pattern? 1 over 0.001, 1,000. Okay, let's quit playing around. 1 over 1 billion. 1 over, there we go. 1 over 1 billionth. 1 billion. Okay? So as the denominator of a fraction gets smaller, what happens to the value of the fraction? Gets bigger. What if the denominator is so small we can't measure it? Then the fraction would be so big we can't measure it, right? Still exists, but it's so small we're incapable of measuring it. Well, what if we actually hit 0? How many zeros are there in 1? An infinite, and you still don't get there, right? 0 plus 0 plus 0 plus 0 plus 0. You line that up for infinity, and you still won't reach 1. So tangent of 90 is actually infinity. So the wall is infinitely longer than the ground. Okay? And then that last question on that page, you can scribble that out. But before you turn the page, I want to show you something. You might not have noticed. If the ladder is length 1, sine is the wall, cosine is the ground, and tangent happens to be wall over ground, therefore, tangent equals sine over cosine if the ladder is length 1. Everybody see that? Because normally, sine is wall over ladder, and cosine is ground over ladder. But if the ladder is length 1, then I can erase those ladders, and we just get wall and ground. Tangent is wall and ground, therefore tangent is sine over cosine. What if the latter is not length 1? Well, let's try it. Sine equals wall over ladder. Cosine equals ground over ladder. If I divide those two, how do you divide two fractions? You flippin' times, as Tom Hansen likes to say. So you flip the bottom one, L over G. What do you notice? The L's cancel, and I'm left with, which is, so you have a tangent button on your calculator. If it were to ever break, you don't need it. If you want the tangent of 10 degrees, take the sine of 10 degrees and divide it by the cosine of 10 degrees. That will always work. Okay? Well, you're going to see in a minute that you don't even need a cosine button. If your tangent is broken and your cosine is broken, you're okay. As long as you have sine, you can do all 6 of the trig functions. If sine, cosine, and tangent are broken, you're in trouble. If you need either sine or cosine, if you had sine or cosine, that's enough. Tangent is not enough. Unless, if you had tangent and sine, then you're okay, because you have sine. Well, as long as you have cosine, you're fine. Okay. So, turn the page again. For what value of theta will the sine of theta equal the cosine of theta? Is there a triangle so that the sine and the cosine are equal? When? Right. This only happens at 45 degrees. Why? Because be more specific, the wall equals the ground. So the wall length equals the ground length. Now I'm curious, don't calculate this. What is the percentage at 45 degrees? A lot of people think 50%, but it's not. It's got to be bigger than 50%. So let's try it. So the sine of 45 is 70%. Why did it have to be bigger than 0.5? Right. If you had two legs of a right triangle that were 0.5, the hypotenuse could not be 1. Right? So we need to draw this picture. If that's 1 and this is 0.5 and this is 0.5, those lengths aren't long enough. Right? Because they add up to be 1, so one of them would go there and one of them would go there. So what did we just learn about the sine of theta plus the cosine of theta? Then, well, that is true in this case, 50%. So we just learned that the sine of theta plus the cosine of theta has to be bigger than 1. Right, 0.7 plus 0.7 is bigger than 1. Right. Good. And that's, so this is always true because that's talking about percentages. Okay? But what Peyton is saying is if this is 1, then these add to be bigger than 1, which is also true. Yes. It wouldn't, if they were both 0.51, then that 90-degree angle would end up being not 90 degrees. Because, so if I had 0.7 and 0.7, if I kept this at 1, then that would suck those sides in, and that angle would become bigger than 90. That's true. Yeah, so if that's a 4, then this plus that would have to be bigger than 4. That's true. That's also true. Okay, so I hope you drew that picture with the point sevens. Yeah. When in doubt, draw a picture and bring Mr. White a box of cookies. Okay, so what is the value of the tangent when sine equals cosine? Why 1? Because wall and ground are equal, and anything divided by itself is 1. Yes. So the answer to that is 1, because the wall is 100% of the ground, because they're the same length. So can the tangent be bigger than 1? Yes. Can the sine be bigger than 1? No. Can the cosine be bigger than 1? No. Can the sine be smaller than 0? Not today. Stay tuned. Okay, how do sine and cosine relate to each other within the same triangle? Well, if we were to look at this, as I pull that ladder away from the wall, what happens? Okay, we're not talking about the angles, we're talking about the side lengths. So the wall corresponds to wall. What ratio is the wall? Sine, if the ladder is length 1. So as the sine gets smaller, the cosine gets bigger. Don't write that down yet. Okay? Right. What if we started at the end and worked backwards? So if sine goes down, cosine goes up. If cosine goes up, sine goes down. Don't write that down yet. Okay? Could we be more specific about how they relate to each other? Opposite how? Ah, that's the key. Hopefully I kept this. All right. So I have here a bunch of sine calculations. Sine of 0 is 0%. Hold on, not yet. Okay, everybody agree? Okay, I plug in all those sine values and I get percentages from 0 to 1. Now here's something interesting. Notice this is halfway between those, and yet that is not halfway between those. That's kind of weird. It went up really fast and then it started slowing down. It's not exponential, it's slowed down. Exponential doesn't ever slow down. It speeds up. Okay? So this started off really steep, and then it started to level off until it hits 1. So it went something like this. It started steep, and then it started slowing down. Just wait. Okay, well, here is the domain of sine. Here is the range of sine. Could I create a list of cosine domains that match up with these same ratios? Any more specific? Well, I'm going to use this as my range. So how do I want to arrange my domain? Start at 90, 75, 60, 45. Now, before I draw the lines, is that true? We said as sine goes up, cosine goes down. But the question is, do the percentages match? How do you know? Okay, so cosine of 90 is 0. All of these match. We need more Connor Shushers in this life. So, here's the question. Why is that true? You already know the answer. You just haven't realized it yet. We've talked about it multiple times. Okay, so the fact that one goes up, the other goes down is seen in this picture. But this does not explain why as one goes up, the other goes down in the exact same fashion. Why is that the case? Ah, that's the key. So, if this angle here is theta, what is this angle here? 90 minus theta. And this is where the word complementary comes in, right? These two angles are complementary. They add to be 90 degrees. So sine and cosine are complements of each other. If you notice, 60 and 30 add to be 90. 15 and 75 add to be 90. And that's true with all of them. So the answer here is they're complementary. And what I also want you to write is the sine of theta is equal to the cosine of 90 minus theta. Now, you want to see that in picture form? Well, you already saw it. So, what is the sine of theta? Well, it's going to be adjacent over hypotenuse. Or, sorry, I got that wrong. So, it's going to be opposite over hypotenuse. Okay? What is the cosine of 90 minus theta? It's the same ratio. So the sine of this angle is the left side divided by the hypotenuse. The cosine of the other angle is the adjacent over the hypotenuse. It's the same ratio. So that's why we said earlier that the sine of A equals the cosine of B, because A and B add to be 90. Okay? Now, don't get that confused. That doesn't work with the percentages. It only works with the angles. Does that make sense? So the percentages are different. The percentages have to be bigger than 1, right? So if you take the sine of an angle plus the cosine of the same angle, the percentages have to be bigger than 1. Okay? All right. This one trips people up, but it's super easy. You just freak yourselves out. When will 2 sine of theta equal the cosine of theta? Yes? No. No, that's not true. So, well, remind me, what does sine of theta mean? No, it's simpler than that. No, what does sine mean? In this triangle, what does sine mean? Wall over ladder, but the ladder is length 1. It's just the wall. So this is the sine. What does the cosine mean? So when does 2 sine equal cosine? When the wall is half the ground. So if I know that this is twice as big as that, how do I calculate theta? So all you know, I've given you a triangle. If this is x, then this, nope, other way around. If this is x, then this is 2x. How do I calculate the angle? It's not 33. Because remember, the angle relationship is different from the side relationship. If the side relationship is 1/2, the angle relationship will be close. No. Well, we've forgotten a really important rule. Does the size of the triangle affect the angle? No. So it doesn't matter how big we make this. So let's make this 40. Well, if that's 40, then this is 80. Now, how do we calculate that? Inverse tangent. So, inverse tangent of 40 over 80. Could I have used a different value? So, I could do the inverse tangent of 0.5. I could do the inverse tangent of 3/6. Because that angle stays the same as long as the triangle is similar. You could use 1 and 2. Yeah. Because the tangent doesn't care how long the ladder is. All right. We're almost done. Is that okay? So for the sine, the cosine, and the tangent, that's what we just did. No, it's just 26 degrees. Yeah. All right. What are the inputs for sine, cosine, and tangent? What do we stick in? Angles. So these are angles. What do we get out, Connor? Percentages, unless the ladder is length 1, and then we get percentages and side lengths for the sine and the cosine. Yeah. Okay, so the domain of sine we have extended. It used to be greater than 0, less than 90. It's now from 0 to 90. What are the outputs? What is the range? How small can sine be? 0. How big can it be? 1. Do we include those values? We do today. Yesterday we didn't. So from 0 to 1. How about the cosine? What's the domain? 0 to 90. And the range? And really it's 1 to 0, but we just always keep them in order. So it's 0 to 1. Yeah. Sine and cosine are actually, they have the same domain and the same range. What about the tangent? Okay, hang on a second. We got to get this finished. What can we plug? What angles can we plug into tangent? From 0? No. Right, we can't hit 90 anymore. Because when you plug in 90, you get infinity. So from 0 to 90, non-inclusive. Because that 90-degree angle creates an undefined line. So what's the range? 0 to infinity. No, yeah, good luck. If you can capture infinity, let me know. I think infinity's out there by the perpetual motion machine. Okay, so the last question asks, explain to me again why we like the ladder length 1. That doesn't work, because this question will be on the test. Percentage equals the length. That's the first answer. But sine becomes the wall, and cosine becomes the ground. Percentage becomes the length, and sine is wall, and cosine is ground.